So this is not really a new finding in climate science, climate change as such, but it's still an important topic because climate models are used routinely for predictions, for projections, and there is always this argument about resolution, whether they have high enough resolution or if they are covering every aspect of the biogeochemistry, human influences and human agency into the Earth system. You have atmosphere, ocean, land, cryosphere, and you have some way of representing human activities, and then you need the chemistry, greenhouse gases, carbon cycle, dynamic vegetation. It looks very complicated, so the question is, despite the complexity of the Earth's climate system, can you actually detect, identify and predict human activities? This is an older article from 2005 or so by Isaac Held, who argued that there is simplicity amid complexity, and he says despite the complexity of the Earth's climate system, the influence of human activities on climate can be identified and predicted. So 20 years later, 15 years later, is that still true? Well, people will argue that we are not doing so well, but Isaac Held is a very intelligent, wise man of the business. He's retired, but he's still around to give us some wise words. So let's read what he was having, what he thought at that time. We live in interesting times as we watch diverse effects of human activities on Earth's climate emerge from natural variability. So we have been observing natural variability through paleoclimate evidences, direct evidences, and so on, and then we started seeing the change, trends, extremes, and so on, and he's saying now they are becoming more and more obvious as jumping outside the natural variability. In predicting the outcome of this evolving inadvertent experiment of increasing greenhouse gases, climate science faces many challenges, some of which have been outlined in this series of science perspectives. Reducing the uncertainty in climate sensitivity, explaining the recent slowdown in the rate of warming and its implications for understanding internal variability, uncovering the factors that control how and where the land will become drier as it warms, quantifying the cooling due to anthropogenic aerosols, explaining the curious evolution of atmospheric methane. Unlike CO2, methane doesn't increase, it flattens out, then it jumps up. We don't always know what's happening, just in terms of sources, sinks, and so on. So predicting changes in extreme weather is another big challenge. In addition to these challenges, the turbulent and chaotic atmosphere and oceanic flows seemingly limit predictability on various time scales. Is the climate system just too complex for useful predictions? Just jumping ahead, I'm going to just take few words from this. A creative tension between simulation and understanding, between accepting complexity and searching for simplicity, is present in many challenging scientific problems. Climate science provides an excellent example of this tension. The most advanced comprehensive climate models effectively represent the current ability to simulate the climate system, and it is natural and appropriate to take the output of those models as the basis for predicting the future climate. However, it is the understanding of these responses, an understanding that depends on the presence of an emergent simplicity in the forced response, which provides a level of confidence that justifies advising policymakers and the public to pay heed to these predictions. That's a long sentence, but basically forced response means as we increase CO2, we are changing the radiative balance and we are forcing an imbalance and we are forcing the climate. So is there an emergent simplicity? And there is. By now we know that, for example, the global mean warming seems to be linearly proportional to cumulative CO2 from the beginning of the Industrial Revolution. So you know know that no matter where you add a ton of CO2, when you add it, it's going to show up in the warming in a linear way. That's simplicity. But then if you zoom out and look at the patterns of warming and patterns of changes in drier land, extreme rain, and so on, it's anything but complicated. So how do you produce information for policymakers, especially to invest in solutions, adaptation, mitigation? You need local information. How do we do that? So let me yell at this guy who is shouting outside. So we need to worry about then models. Can they be very complex models? Can they be very simple models? Do we need a hierarchy of models? That's the key question. That's the topic of this podcast. Maybe there'll be more than one. The gap between simulation and understanding in climate modeling. This is again Isaac Held. Should we strive to construct climate models of a lasting value, or should we accept as inevitable the obsolescence of our models as computer power increases? In other words, we started with simple coarse resolution, well, simple in some sense, coarse resolution models in the 1960s, and then we kept on adding complexity, increasing resolutions as the computer power evolved. And now we have added another complexity. Before Isaac Held wrote this, this was not so obvious. We are adding AI and ML, artificial intelligence, machine learning, as a part of improving the models and just directly modeling. So I have a podcast just before this talking about AI for predicting weather, climate. Now there are also for hurricanes and so on and so forth. So here is an example of simple GCM that Dargan Frierson of University of Washington did, where you're looking at instantaneous precipitation over the globe from 3 versions of an idealized moist general circulation model using 3 convective closures. A lot of technical words, but basically convection in the model to produce rainfall is not explicitly resolved, so we parameterize it. So we used data and so on, and we do convective closures, which is an assumption. So sometimes you're explicitly resolving convection, but for that you need a resolution that is high enough to capture convection, which tends to be very small scale. The idea here is that you can use idealized general circulation model, which means it'll run faster and yet try to produce things that are realistic. But the question is, you can see that this is an idealized channel model and doesn't have land, doesn't have ocean. It's like an aqua planet, let's say, where everything is water. Then you have resolved, let's say, statistical properties of instantaneous precipitation over the globe. Then how do you then translate it to actually forecasting rain or understanding how rain may change in the future? That's where you need to meet policymakers and human beings, right? So this is the same idea of thinking about elegance versus elaboration. So let's say this is elegance, and it's idealized, so it can be run again and again, and many things can be learned. But what about elaboration? So the future of climate theory, according to Isaac Held, then accepting that the construction and analysis, is this a different paper? Let me make sure. No, it is the same. Accepting, because I'm going to read another paper on hierarchy of models, accepting that the construction and analysis of climate model hierarchies yields important understanding, and given the many efforts underway devoted to models of various levels of complexity, can this effort be made more productive? I highlight 2 related tendencies that have slowed the systematic development of climate model hierarchies. So Isaac believes in hierarchies of models to understand. So my own work illustrates these tendencies nicely, and this discussion is as much self-critique as it is one of the field more generally. So we are worrying about elegance versus elaboration. So our goal must be to reduce the number of idealized models that we analyze. Otherwise we are left with a string of more or less interesting results, few of which have been intensively examined by more than 2 or 3 people, and that we never quite managed to relate to each other. Furthermore, when models are analyzed and not reproduced by others, we are never certain that the computations have been performed properly. But how can this inefficient deployment of our theoretical resources be avoided? It's okay to say avoid them, but how do we avoid them? The key, I feel, is elegance. An elegant model is only as elaborate as it needs to be to capture the essence of a particular source of complexity, but it is no more elaborate. It's kind of an Occam's razor principle. Many of our models are more elaborate than they need be, and this is, I believe, the prime reason why it is difficult for the field as a whole to focus efficiently on a smaller number of models. So a general circulation model wants to include everything: land use, orography, ocean, atmosphere, chemistry, and sometimes vegetation, dynamics, and so on. Does that just make things too complicated to understand? That's what this argument is about. So small number of efficient models. If a particular scheme seems unnecessarily baroque, why should I use it as a basis for my own research? What lasting will my study have? We all want our work to be relevant to the big issues on in climate dynamics. This relevance requires a certain level of realism in one's simulations, and the pressure to reach the required level of realism pushes models toward an ever-increasing elaboration. Yet, in the process, one's model often loses much of its attraction to other researchers who may not be in agreement with all of those choices made in the process of elaboration. So you get the idea. He's trying to find a compromise between having realistic models that can actually predict something that is observed, not necessarily everything, let's say something, versus understanding something like what you are doing here, understanding the precipitation process versus predicting monsoon over India. So he concludes that the health of climate theory and modeling in the coming decades is threatened by a growing gap between high-end simulations and idealized theoretical work. In order to fill this gap, research with a hierarchy of models is needed, but to be successful, this work must progress towards two goals simultaneously. It must, on the one hand, make contact with the high-end simulations and improve the comprehensive model development process. So you're making some process understanding that translates into improving the fully complex model with all the kitchen sink in it. And secondly, so the model development process has to be improved, otherwise it's irrelevant to that process, and therefore to all of the important applications that are built on our ability to simulate at any level. On the other hand, it must proceed more systematically toward the creation of a hierarchy of lasting value, providing a solid framework within which our understanding of the climate system and that of future generations is embedded. Sounds complicated, but now you go online, you will find many Python-based models, simple climate models, atmosphere models, ocean models that you can run, make sensitivity studies, and so on. Does that meet this purpose of hierarchy of models? You have to ask Isaac whether he agrees. Funding for climate dynamics should reflect this need to balance conceptual research, simulation, and hierarchy development. Okay, so I wanted to start with that because this paper came out just recently, maybe this year or last year, which provides a perspective on climate model hierarchies, building on what Isaac said, but they go into more details of complex models and provide a framework in which to look at the complexities and possible pathways to simplification. So they also try to keep Isaac's message in mind in terms of elegance versus computation, whatever he called elegance versus elaboration. So we'll come back and read that. So let's leave this podcast here and see what the young generation has to say about model hierarchies. Okay.